Hi everyone, today we are doing chapter 5.1, which is on exponential growth. Let's consider a culture of 10 bacteria that is placed into a petri dish. The bacteria is expected to grow at a rate of 4.7% each hour. Since we just got done with our unit on sequences and series, let's think about this as a recursive sequence. So my initial amount, A sub 0, is 10 bacteria. And then at the nth, it looks like at the nth hour, because it's increasing by 4.7% each hour, A sub n for the nth hour is equal to A sub n minus 1, the number of bacteria in the previous hour, times 1.047, such that n is greater than or equal to 1. Now when I'm multiplying by this 1.047, remember by multiplying by 1 you get yourself, and then by multiplying by the 0.047 I increase by that 4.7%. So I can just do that in one step. So the question that I have is, what would this recursive sequence look like if I were to think of it as a function? So I'm actually going to make an XY chart. Actually, let's make it N chart, NY chart. Where N is the number of hours that have passed and Y is the number of bacteria. So I know in the 0th hour, there's 10 bacteria. So I'm going to go ahead and plot the point 0, 10. After 1 hour, if I multiply 10 times 1.047, let's see what I get. I've got 10 times 1.047. And I get 10.47. So after 1 hour, I don't quite have 11, I just got a little more. After 2 hours, I have 10.9621. 2 hours, I've got still a little bit more. After 3 hours, let's do it again. Again, I'm just multiplying by 1.047 every single time. I get 11.4773. So finally, a little bit more. Let's look at 4. I get 12.0168. And let's do one more. 12.5815. So here I'm at 12.5815. So you can see that we're not growing linear here. Every single time that I go from one step to the next, the step gets a little bit bigger every single time. That jump is a little bit bigger. It's not going to be the exact same. What about after 10 hours? Do you think that instead of multiplying by 1.047 10 times, there might be an easier way that I can think about this? And the answer comes from the explicit formula for this. So since this is geometric, which we know from the last unit, with my common ratio of 1.047, I know that the form A sub n is equal to my initial condition times 1.047 raised to the n is the explicit formula. So what I want to do is I just want to plug in 10 for n, and then I can see how many bacteria there are after 10 hours. So I'll have 10 times 1.047 raised to the 10th, and I get 15.8295. So I jump, up here to about 15-ish. So when I look at this function, I can see we get an exponential growth curve. And exponential growth curves are going to look very similar to geometric series where that common ratio is greater than 1. They're going to look like y equals some a value times b raised to the x, where that b value is greater than 1, and my a is going to be my initial amount. So a I'm going to run out of space here. A is usually equal to this initial amount, the amount that you start with at time 0 is usually what we've got here. So that's the general form for exponential growth. Again, y equals a times b raised to the x such that b is greater than 1, and a is my initial amount. So now let's take a look at some very specific forms of exponential growth, similar to my bacteria problem here. Oh, and I guess maybe what I could do, let's write this as a function just while we're here. So if I was going to model this bacteria problem here as a function, I'd have y, the amount of bacteria, is equal to my initial amount, 10, times my b is 1.047 raised to the x. So this would be my model for the bacteria. It's worth noting that this right here, the b value, is called the growth factor. And the growth factor is different than the growth rate. R is equal to the growth rate, and b is always equal to 1 plus r. So you'll notice my growth rate here is 4.7%, so that's the 0.047, and if I add 1 to that, I get the growth factor of 1.047. All right, so annual compounding. Often, especially when we're talking about money, you will have money invested into a bank account or some form of investment such that it will grow at an annual rate and interest will be compounded and added on every single year. So if that is the case, then A is equal to P times 1 plus R raised to the T. And notice this is this mirrors my exponential growth model that I had in the last example, and I'll show you how. So this A is going to stand for the amount in the account after T years, usually T years. It could be a different form of time, but usually it's years. And that A is the same as this Y right here. The P, we use a P because it stands for principal. The initial investment, or the initial amount, which is the A here. 1 plus R. R is going to be that growth rate. And this 1 plus R here is like this B right here, because B is equal to 1 plus R. And then T stands for time that has elapsed, and that's the same as this X right here. So it's when I do annual compounding, I'm really just have an exponential growth function, and I'm just putting very specific letters in to stand for what I'm talking about. So my example is $1,000 is invested into an account earning 6% annual interest. How much will be in the account after 5 years? So I want to know how much is in this account. So A equals my principal is 1,000 times 1 plus my rate is 6%, so 0.06, raised to T, which is 5. And when I plug this in my calculator, I get $1,338.23. Not too bad. Let's look at the next problem. It says the value of an antique ring is said to increase by 8% each year. If the ring was purchased in 1940 for $12, what is the value of the ring today? So I want to know the value of the ring, or the amount that it's worth. The initial principal or investment or worth was $12. It will increase by 8%, so I get 1 plus 0.08. And then how much time has elapsed from 1940 to 2019? It's 79 years. So when I plug this into my calculator, the ring is worth $5,243.94. I sure hope that my grandma held on to whatever ring this is. All right, so banks also will offer interest compounded at multiple times per year, or n times per year. The last one we talked about, it was only compounded once a year. But if they compound n times per year, and they usually tell you how often that's going to be, our formula changes just a little bit. So I still have the amount that's invested, which is equal to the principal times 1 plus, now instead of the rate, the whole interest rate, you don't get the rate at one time. You get it in increments of n. So it's going to be the interest rate that you have divided by n. And since it's split up into n increments, you're going to raise that to the n times t. So really, the only thing changing here is I'm adding in these n values, where n is equal to the number of times interest is compounded each year. So let's look at this example. You invest $1,000 earning 6% interest compounded quarterly. So if it's compounded quarterly, that means 4 times per year. How much money will you have after 5 years? So the only thing I've changed from the example on the last slide is that it's compounded quarterly. So let's see if this makes a difference in how much money you have. So I'll have A equals 1,000 times 1 plus my interest rate, 0.06, divided by 4, raised to the 4 times 5. Be careful if you're going to plug this into your calculator all in one step. Make sure you add parentheses around this fraction right here. So when you do this, you end up with $1,346.86, which is a little more than what you had when it compounded annually. I had $1,338.23. My bad. When I compounded annually. So this was the annual compounding. So why do you think that you have more money when you're compounding quarterly? Well, the answer is because you compound at that first quarter and they add on the interest. So then you're going to get interest on that interest that was added in. And that's going to happen 4 times throughout that year. So that is why you end up with a little more money. What is the end value if the interest is compounded in the following increments? So yearly, the end value is obviously one time a year. Monthly, there's 12 months a year, so monthly the end would be equal to 12. Weekly, there are 52 weeks in a year, so that would be that end value. And daily, we're going to go ahead and go with 365. We know that there are leap years where there's 366 days, so we're just going to use this 365. All right, so what happens if you compound interest continuously, meaning all the time? So at this point in class, we did an investigation using Excel, and what we did was we set up a few columns, and we basically looked at what happens to this as I drag the end value to infinity, what happens to my investment if, let's say investment, if I were to invest $1 into an account that pays 100% interest for 1 year. So I'm setting everything but the end value. So I'm saying my amount is equal to 1 times 1 plus 1 over n raised to the n times 1. I don't know why I just did that. N times 1. So this literally just becomes 1 plus 1 over n raised to the n. So we set up a column for the n value, and we just started with 1, and we dragged it down, and then we set up A and used a formula dependent on the column to the left. Set up my formula and dragged it down, and what we saw was that A never exceeds 2.7182 dot dot dot, and a lot of you noticed this is E. So this helps us understand a little bit where the next formula comes from. And if this didn't make a whole lot of sense to you, I encourage you to open up your Excel file and take a look at what happens as n gets really large, as it approaches infinity. So this helps us understand this next formula of continuous compounding. So sometimes whenever you're reading an example, it will say that the interest is compounded continuously. And what that means is your formula changes just a little bit again to A equals P times E raised to the R times T. Remember that P is just my principal. E is just a constant. It is equal to about 2.71828 dot dot dot. It is irrational, so that never ends, never terminates, never repeats. My R is still going to be my interest rate, and T is still time. So based on our first example where we compounded interest annually, my second one where I compounded quarterly, and now I'm going to compound continuously, what do you think about how much money I'm going to have if I invest $1,000 at that 6% interest rate and I'm still going to invest it for 5 years? Do you think I'm going to have more or less money? Well, let's find out. So if I have that $1,000 times E raised to the 0.06 times 5, let's see, I end up with $1,349.86. So notice that is more than quarterly, and the quarterly was more than the annually. So the more times I compound interest, the more money I'm going to have in that account. All right, let's look at one more example. It says, at present, the population of Gambia is about 2.05 million people. The population is growing at a rate of 3.22% compounded annually. If the population continues to grow at this rate, what will the population of Gambia be in 10 years? So I added a map for you here because Gambia is a very small country on the western side of Africa. And the population growth is this 3.22%. And my question is, do you think that is a large percent increase for a country like Gambia? Well, so it says that population is growing compounded annually. So the amount of people is going to be equal to 2.05, my initial amount, million, times 1 plus 0.0322 raised to the t, which is 10 years. So if I plug this into my calculator, I end up with 2.81, and that is in million people. So back to the original question, is 3.22% a large percent growth for a country like Gambia? I think so. 2.05 to 2.81 million people for this small country in 10 years seems like it's going to put a big strain on resources. I think that but that population growth rate is pretty large for that country. It said, the next question says, what if the population was growing at a rate compounded continuously? How different would that population approximation be? So my formula would change a little bit. I'd have 2.05 times E raised to the 0.0322 times 10. And if I do that, let's see what I get. I get 2.05 times E, and then 0.0322 times 10. I get about 2.83 million people. So you can see there the change here comes in the hundredths place. And when I'm dealing in millions of people, that is a pretty significant increase considering I'm talking about millions of people. So that concludes the lesson for today. You guys are now all set to do problem set 5.1.